Okay, today we're going to talk about independent and dependent events. So we've been talking about probability, and we've been asking questions like, what's the probability of flipping a coin, here's my coin, and getting tails? What's the probability of doing that? And now the sort of question we've been asking is, what's the probability of spinning this spinner that I'm drawing right here? What's the probability of spinning this spinner and getting a 3? So today what we're going to learn is, what if you wanted both those? What if I was asking you, what's the probability of flipping a tails and spinning a 3? Why did I say 3 and put it pointing to a 2? That's really pathetic. Let's change it to 2. What's the probability of flipping tails and spinning 2? Okay, that's what we're going to talk about today. So the first thing we have to talk about is the difference between independent and dependent events. Today what we'll be concentrating on is independent events, and then we'll do dependent events next day. So independent events are events when one event occurring does not impact the probability of another event occurring. So for example, let's go back to this, what we did right here. Let's say I'm interested in getting orange and the number 5 on this. Okay, now I want both those things to happen. I want to get orange and I want to get 5. So whatever I get on this spinner right here, orange would have been nice, but the fact that I got pink, does that impact the probability of what I get over here? No, it doesn't matter what I get here. I get pink here, I get this blue here, I get an orange here. Yes, whatever I get, it makes no difference to the probability here. The probability of me getting a 5 here is still 1 out of 6, right? No matter what happens on the spinner, it has no impact on the probability of getting a 5 or the probability of getting a 3 here. So independent events, one event has no impact on another event. Example, flipping a coin and rolling a die. If I flip a coin, whether I get heads or tails, that does not impact what I'm going to get on the dice, on the die, right? I got one other thing to say, but I'm going to come back to it. So as you could probably guess, with dependent events, one event occurring impacts the probability of another event occurring. So an example of that would be something like this. Let's say you have a bag of marbles. I could actually draw this, I suppose. I have this terrible way I draw bags of marbles. It looks something like this. And then you've got some marbles in here. You've got 2 green ones, and you've got a purple one, and you've got a yellow one. Okay, oh, it's hard to see the yellow one, but it's there. So let's say that you pull a marble out of the bag, and then you're going to pull another marble out. So let's say we reach in and we pull out a purple one. And then I want to know, what's the probability of pulling out a green? Now, is the fact that I took that marble out, does that impact the probability? It sure does, right? If I put it back in at this starting point, what was the probability of pulling out a green if I randomly picked out of here? I wasn't looking and I reached in. Well, there's 4 total here. The probability originally would be 4 total. So that's our bottom number. 4 is the bottom. That's the total. And how many are favorable if I want to pick green? Well, there's 1, 2 greens. So it's 2 over 4, or we could put it in lowest terms, 1 over 2, right? Okay, but now, what if I started this, my first event was actually to pull out a marble, and I happened to pick out the purple, or maybe I happened to pick out the yellow, or maybe I even happened to pick out one of the greens. But let's just say I picked out the purple. Does that impact the probability of now getting a green? Well, let's see. If I reach back in, this thing's gone, right? I threw that away more or less. So if I reach in here, now how many are there to choose from? There's only 3. And how many favorable ones are there? There's still 2. So now, instead of having a probability of 1 out of 2, 1/2 of getting green, I have 2/3 of getting green. So I have a better probability. This is dependent. If you take something out of the bag and don't replace it, then it's going to be dependent. But if I did the same thing and I replaced it, right, this is why I put this in big bold here, then it is an independent event. Because let's do this whole idea over again. If I started here and I wanted to know what the probability of green is, it would be exactly the same, 2 out of 4, right, just like it was before. And then if I reach in, just like I did before, and I pull out a purple, and I replace it, and then I pull out the second marble, what's the probability of getting green? Well, it's still 2 over 4. Effectively, we're back to the original state. Okay, so this replacing and not replacing is a big part of independent and dependent. And you'll see lots of other examples too. Could even be examples in real life. Does the probability of it raining, is an event like it raining, does that impact what I have for breakfast? Well, probably not. I mean, maybe there's some weird condition where I don't eat cereal if it's raining, but I doubt it. It probably doesn't impact. So those are independent. Does the fact that it rains impact the probability that I go for a bike ride? Yeah, it does. It's not quite as much fun to ride in the rain, so those would be dependent events. Hopefully that makes sense. So today we're going to focus on independent. And the main thing we want to come up with is how do we get the probability of two things occurring? So, for example, if I wanted to know, let's do this question right here. If I wanted to know the probability of getting tails on a coin and rolling a 5 on a die. Now, one way we could figure this out is we could do a tree diagram. And I'm going to do a tree diagram. But this will be the last tree diagram we'll probably draw for a while because I imagine lots of you don't like the tree diagram. We wish there was a faster way to answer this question without drawing a tree diagram. And there is, don't worry. So we'll do the tree diagram and then we'll figure out what the faster way is. All right, so tree diagram. Flipping a coin. So we got a coin and we got our die. Remember, you don't do this. Wrong. No, do not do this. Coin, die. No, that is wrong. Okay, what you want to do is you want to think of one of those things to start. So why don't we think of the coin? If you think of the coin, how many different outcomes are there? There's two outcomes, right? You could either get heads or you could get tails. Great. Now we're going to think of the die. Right? If you want, just like I did before, you could put coin here and die. Die. You could put die there. Okay. If you think of the die, how many different outcomes are there? 6. 1, 2, 3, 4, 5, and 6. So how do we do this? We draw 6 lines coming out of here. Oh gosh, this is going to be squished. 5, 6. And we draw 6 coming out of here. 2, 3, 4, 5, 6. All right. So we're going to have 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. Great. So now what we want to know is what's the probability of flipping tails and rolling a 5? So which one of the pathways is that? Flipping tails and rolling 5. There's only one that works right there. Tails and 5. So what's our probability of doing that? Well, how many different outcomes are there? Remember, we look out here to count the outcomes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 outcomes, so we put it over 12. And there's only one that actually works. So our probability is 1 out of 12. Now, again, I don't want to have to draw a tree diagram. I kind of like it, but I know most of you don't. So let's see if we can figure out how to do this without doing a tree diagram. Let's figure out, first of all, the probability of flipping tails on a coin. So what's the probability of getting tails? Well, if you flip a coin, how many outcomes are there? 2, heads and tails. How many of them are favorable if we're trying to get tails? Just one, the tails. So that's the probability of getting tails on a coin. Now we want to figure out what's the probability of getting 5 on the die. Okay, well, how many outcomes are there when you roll a die? 6. 1, 2, 3, 4, 5, 6. And how many of them are favorable? 1. Just the 5 is favorable. So we're left with this 1/2 and this 1/6, and our answer is 1/12. Can anyone out there see what you could do with the 1/2 and the 1/6 to get the 1/12? Yes, I hear you. I hear you saying it. You are saying multiply those two together. 1/2 times, if you want to put the times sign, whatever way you want to put it, I don't care. But if you multiply those two individual probabilities together, you'll get the probability of both of them occurring, right? Of flipping a coin and getting tails on the coin and rolling a 5 on the die. So this is the most important thing we want to know today. When two events are independent, the probability of both occurring is this. The probability of A and B, so those are two events, A and B, is the probability of A times the probability of B. You just take the individual probabilities and you multiply them together. You don't need to draw a tree diagram. You don't have to do any of that stuff. You just find the individual probabilities and multiply them together, and that'll tell you the probability of both the things happening. Okay, so let's try some questions. First question. A card, our cards. A card is drawn from a deck of cards and replaced. That's good. That means it's going to be independent. And then a second card is drawn from the same deck. What's the probability of getting a 7 and then getting a jack? All right, so first of all, we got to figure out what's the probability of just getting a 7. Just worry about that for now. And then we're going to worry about what's the probability of getting a jack. Okay, how many sevens are there in a deck of cards? There's 4. There's a 7 of hearts, there's a 7 of spades, a 7 of diamonds, and 7 of clubs. So there's 4 favorable outcomes. How many outcomes total when you deal with cards? 52. There's 52 cards in the deck. And remember, you can simplify this. Might as well do it. Make it a little bit easier for the next step. 4 over 52, you can divide them both by 4. You get 1 out of 13. All right, what's the probability of getting a jack? Well, it's very similar. How many jacks are there in the deck? 4. Jack of hearts, jack of diamond, jacks of club, jacks of spades. How many cards total? 52. Put it in lowest terms, 1 out of 13. So the probability of getting a 7 out of the deck is 1 out of 13. The probability of a jack out of the deck is 1 out of 13. What if we want to know what the probability is of getting the first card a 7 and the second card a jack? All you have to do is multiply those two things together and you will get your answer. The probability is 1 in 169. It's not very likely that it's going to happen. It could, but it's not all that likely. Number 2. A bag contains 5 white marbles, 3 black marbles, and 2 red marbles. A marble selected at random, then replaced. Thank goodness it's replaced. If it wasn't replaced, like we'll do next day, it would be dependent. A second ball is then selected. Find the probability that 2 white marbles were selected. Alright, so what we need to do is find the probability of getting a white. And then we have to find the probability of getting a white. Well, it's going to be exactly the same, isn't it? It's kind of silly, but let's do it. So, what's the probability of getting a white? Well, how many total outcomes are there in this bag? We have 5 of these, we've got 3 of these, and we've got 2 of these. For a grand total of 10. So that's the total outcomes. How many are favorable? Well, we want white. And how many white are there? There's 5 white. So 5 out of 10. Oh, 5 out of 10. Let's put it in lowest terms. 1/2. So we pick out our marble, then we put it back in, we replace it, and we're back with the original scenario. So what's the probability next time? Exactly the same, 1/2 again. So what's the probability of getting the first one white and the second one white? What do? We multiply them together. 1/2 times 1/2 equals 1/4. Okay, we want to try getting a red, then a black. How do we do it? We've got to get the probability of a red. We've got to get a probability of black. So how many marbles are there? Well, it's the same. We start with the 10 marbles. And how many favorable ones are there if we're looking for red? Red, 2, right here, 2. 2 over 10, put it in lowest terms, 1 over 5. Okay, now what's the probability of getting black? 10 total, because we replaced it. We put that first one back. So we're back to the original scenario, 10 of them in there, and how many are black? 3. Can we put that in lowest terms? No, can't do anything else. So we're ready to multiply. Probability of getting the first one red is 1/5. Probability of getting the second marble black is 3 out of 10. And we multiply those together to get our answer. We get 3 out of 50. And that's in lowest terms. Nothing else you could do. All right, real world question here. I don't know what the answer is yet. I just made up the question. Real numbers here. Steph Curry's free throw percentage. This is for you, Yvonne. Steph Curry's free throw percentage is 90%. He's actually got, I think, the second best right now. Steve Nash, Canada's own Steve Nash, has the best all-time career. The worst free throw percentage for someone who played a significant number of games is Ben Wallace. He was a good player, but his free throw percentage is terrible. 42%. That's awful. If Steph Curry's fouled, what's the probability that he sinks both free throws? So it's a shooting foul, and Steph Curry steps up to try to sink both free throws, 2 free throws. So what's the probability that he makes the first free throw? I'll put probability of the first. Probability of the first is 90%. I'm going to write it as a decimal. It's going to make it a little bit easier. What's 90% as a decimal? Remember, you move it over 2 spots. 0.9. You could also write as a fraction, 9 over 10. Maybe you want to do that. But I just want to show you can do it with percentages. So we got 90%. What's the probability of him getting the second one? Well, does the fact he got the first one impact how he does in the second one? You could probably argue yes, it does, right? You could probably argue he's more confident if he gets the first one or something like that. But let's just pretend for this question that it's independent. Whether he makes or misses the first one, it doesn't impact the second one. I mean, Steph Curry is so good at making free throws, it probably doesn't. If he misses the first one, he's probably like, oh well, I'll make the second one. Ben Wallace might not be that way. He misses the first one and he might be like, oh no, I'm going to miss the second one too. I suck, or something like that. So I think we can say for Steph Curry, the probability again for the second one is 90%, or if I rose a decimal, 0.9. So what's the probability he makes two of them in a row? Well, what do we do to figure these things out? You take the first probability and you multiply it by the second probability. 0.9 times 0.9 is 0.81, or 81%. It's not as high as you might think, right? It's basically 4 to 5 almost. A little better, tiny bit better than 4 to 5. So if Steph Curry goes to the line 5 times in a game, there's only 4 of the times you'd expect him to make both. One of the times you'd probably expect him to miss a shot. That's still pretty impressive though. Let's see for Ben Wallace. So for Ben Wallace, so this is Steph here, the best, or close to it, and here's Ben, the worst. 42%. So the probability of getting the first shot, 42%. Let's write it as a decimal, 0.42. Probability of the second, again, this might not be accurate. He'd probably get all in his head if he missed the first one. But let's pretend that it's independent and give him another 42% for the second one. So his probability of getting both of them, goes to the line. What's the probability he makes both shots? You got to do 0.42 times 0.42. It's actually going to be a pretty low amount. You get 0.1764 for a percentage of 17.64%. That stinks. I mean, you wouldn't expect him to make both unless he went to the line at least 6 times in the game. He might make both once. This is terrible. So that's how you find probabilities of independent events. Okay, everyone, there you go. That's the first part of independent events. Today we mostly did independent. Next day we'll look at dependent events. Take care.